Aleksander Piotrowski, please welcome.
Привет, ребята. Меня зовут Саша. Я буду говорить об Android. Specifically about Jack and Jill, which is a new toolchain from Google, a new compiler and linker, a new way to convert Java code into bytecode and Android applications. I will also squeeze in a few other things into this presentation, so it's going to be about everything and nothing. And hopefully, at the end, you will learn new stuff. And a small caveat, some of these things are my wild imagination, but hopefully there is some truth there, and it's going to happen sooner or later. So let's start with Android virtual machine so that we are on the same page. Virtual machine on Android is this orange thing, which is on top of operating system. Hopefully, yeah, see the color. So virtual machine is running Android framework and our application. And on Android, we have special kind of virtual machine, which is called Dalvik, and on new devices, it's called ART, Android Runtime. And what's funny about Android and the virtual machine on Android is that a bit different than the virtual machine on in Java world. So let's look how it's different. But before we look at that, a quick introduction, what is virtual machine for. So it's, of course, for managing memory, so allocating and freeing memory. We have a garbage collector here. Virtual machine is also for us to run our application, either interpret the application or just compile the application. So on Android, we had interpretation, then was just-in-time compiler, then was a head-on-time compiler. And I will show you that we are back to square number one, to interpreting our code with the latest, greatest art in preview N, number 3, I think. So, of course, on Android, it's all about being fast, super fast UI, power efficient, with those or without those, and low memory footprint. That's virtual machine on Android, how it should be, and actually how it is. There are some differences between Java and Android virtual machines. There are some important differences here. I will just quickly go through them. One of those differences is basically naming. So with Java, I have no idea what's the name of virtual machine in Java. We have bytecode kept in class files, and there's many class files per application. That's Java, old Java world, and everything's together packed into jar file, right? That's Oracle Java. On Android, we have a name for virtual machine, which is Dalvik, or DART, Android Runtime. All the code is kept in different bytecode format, which is called Dalvik executable. There is one single DEX file for whole application. Of course, there is a superscript there because there is multi-DEX feature. So at the end, we have multiple DEX files. But the idea was to have just one DEX file. And everything on Android is packed into zip file, but it's called APK instead of jar. Last but not least, the same thing, the difference between APK and the jar shown on a picture. It's from official documentation for Dalvik. As you can see, jar file has many class files. Each class file has header and whatnot. With APK, everything is connected, compacted, so to speak, into one DEX file. All the headers are kept as one header. All the strings for all different Java files are kept as one string. So for instance, if in an application I have the same string in two Java files, it's all connected, and I have one ID for that string. So this file is smaller. It takes less memory to keep the whole code at runtime. And last important difference between Java and the last important feature of Android is the difference in the way the virtual machine is. So Java is stack-based virtual machine. So we have a stack at the bottom, some values, and stack pointer. And let's imagine that we want to do add operation. So add operation on stack-based virtual machine, so that's not Android, that's good old Java, looks like this. I need to pop value, number 10, I need to pop another value, then I need to run instruction to add those values, I need to push the result back onto the stack. So I need 4 instructions to do add operation with stack-based virtual machine, and at the end, the stack looks more or less like this. And on Android, it looks like this. It's register-based virtual machine. So let's imagine I still have those 4 values, but this time they are kept in registers. They are named, let's say, V0 to V3. I went with V because this is how APK tool is calling registers. And the add command more or less look like this. I just ask system to add register 0 to 1 and put the result into register number 2. Result is more or less like this. So I only need one instruction to do the add operation. And of course, there are some benefits for Android because of that. less code, just one instruction instead four. This approach is designed for compilation, just in time with Dalvik or ahead on time with dart. I can apply some more optimization in here. There is better performance. So now on to new features. So now, thanks to the Google hard work at Google, we have Java 8 language features on Android. It's not full-blown Java 8. So what's not available? I was looking for features that are not available. I found this video on YouTube. So at least according to the title, there are at least 55 new features. And of course, Google gave us like 3 of them, or maybe 4. So what is available? More or less, we have interface with default implementation, can be useful. We have interface with static method. This is actually quite useful, like in this example, to create a factory method to build an instance of a particular interface. Small change. And I think the most interesting thing, and the thing that I started, let's say, debugging and hacking to see and understand how it's done in Jack and Jill is a Lambda expression. So with Android, very often we have a listener like this, and we need to create an anonymous class with one method, like in this case, onClick listener with onClick. And with, of course, with Lambda, I can have this in one line. No magic in here. But what's interesting is the way how Java and Kotlin is converting that into bytecode. I will show that in a while because, yeah, this is another example, maybe more interesting, that with Lambda I can basically convert a good old for loop over items into one-liner. Thanks to Eric's Java. Actually, if you're using Eric's Java, most probably this save your day using this Lambda expression instead of writing all those functions with one method or action one functions on subscriber, anonymous classes with on subscribe, on next, or on complete. So yeah, that's another example. But now we have all those new features, and let's see how Jack and Jill is implementing them. And this is my favorite part. It's super complicated about under the hood stuff and with animations. So Jack stands for Java Android Compiler Kit, and Jill is his friend, Java Intermediate Language Linker. The big idea behind Jack, and Google is like, this is their first bullet on Google website about Jack, is that Jack is open source. So basically, you can go online and find source of Jack, which is super easy. Of course, it's not. For me, it took me a whole evening to find the source code because it's not in master branch. So if you find the repo, and you will see that master branch is empty. You have to go to branches and switch to branch called ub-something, and the code is there. No idea why, but the source code is a hidden Pokemon in this repo. Another thing that they are very proud of, that Jack is faster. I guess it's faster because it's meant for Android. It's not meant for Java world, so another nice feature. And of course, Jack is integrated. That's actually quite interesting because I will show that on next slide, I guess, that with old Java, we had Java, ProGuard, we have to convert Java to .class files and whatnot, and with integration with Jack, everything is there. One Jack, with help of Jill, of course, can do shrinking. I think we needed ProGuard for that. Obfuscation, basically, I need ProGuard for that, but there are some companies that just create code that is already obfuscated, like Get, for instance. We need repackaging, so in multi-dex and all this stuff, we need different tools for that, and with Jack, everything is integrated. So how does Jack really work? So let's imagine we have our app, let's say Viber. There's some .java files in our application. And right now with all the toolkit, so with Java-C from Oracle, we just run Java command, and we have .class files. And basically, this is all the Java stuff. On Android, we have one more step. If you enable that or not, we can obfuscate the code and optimize it with ProGuard. And of course, the last missing bit on Android is dex maker, I think, or dx for short, a command that is converting class files into dex files. Like I said, we don't have multiple dex files because we have multi-dex. So at the end, we have something like this. We started with multiple dex files. They were together connected into one, and then with multi-dex, we have many dex files again. So this is more or less how Android is compiling your application using the old toolchain from Oracle. It's from Java code through class files, through smaller class files, and then on into dex file. And let's imagine that we have external library, in our project. So that's typical project that we are working on as Android developers, right? And now how it's different with Jack and Jill. So we still have source code. So we still have our library in, let's say, .class form, and then suddenly there is magic happening. Our code goes straight from Java into multi-dexed, obfuscated, optimized code thanks to Jack. And of course, this external library is being converted into intermediate representation called Joyce by Jill, and then this Joyce is added to compilation project to Jack, that when Jack is converting Java, is also taking those Joyce files and at the end is outputting dex file. And that's big magic behind Jack, which is of course not so true because there is an intermediate step. Let's move aside the Jack. Intermediate step is like this, that the Jill is doing so, let's say, pre-jacking. It's creating also a pre-dexed file and also putting resources there and creating something called Jack library, which is basically, I guess, zip file. Honestly, never saw this file in my project, even when using Jack. But according to documentation, there is this middle step when Jill is doing some extra work so that the Jack is getting a pre-dexed file with Joyce and the resources optimized to speed up all the things. So this also adds this speed up improvement. So that Jack, let's imagine that we have JSON library on the project and we download the library only once and then the version is not being changed so often. So when we convert these libraries from class files into this Jack format library, then it's faster for each compilation just to reuse this pre-dexed, prepared library version. So more or less, this is how Jack is working, and there are some nifty features in here, and this is my wild imagination. So if you look at this diagram once again, and maybe you can see the red dot. Oh yeah. So basically, Jack right now in here, he is working straight on Java file. He is not touching class file. There is no connection in here. Thanks to that, Jack has access to original Java file. So Jack can do the optimizations that Jack, so Google, prefers to do. Before, with Java-C, we had the optimization created by, let's say, Oracle, optimization that were maybe prepared or meant for servers, for Java on server. With Jack, Google can apply optimization specifically for mobile platforms. And actually, if you find this open code on GitHub, no, it's not GitHub, it's on googlesource.com, Android Google Source or something like that. You find the code, there is a directory with optimizations, which are basically Java files. And there are, I think, like 5 or 10 optimizations already there. So Jack is applying Android-specific optimization to the code thanks to the fact that it's working on Java code. Another funny thing about that is that we have Java file in here, and we have Joyce file in here, so we don't have this class file. So there is a less way for Oracle to be like in the way for the whole toolchain. And last thing for me, it's I'm 100% sure that's going to happen sooner or later. Let's imagine that instead of Java files, Jack is reading Swift file. Why not? Jack could read Swift file and convert that into a DEX file. Why not? It's possible. It's just like with GCC, you have front end and back end, a part of a compilator. So you can have different front ends to read Java, Swift, or maybe even Kotlin. So like I said, it's going to happen next year, and just like wait for Google I/O, they will announce that soon. So now the most scary part, Lambdas. So Lambdas are this new Java 8 language feature, and we have also Jack, which is needed for us to use Lambdas on Android, if we don't go with retro Lambda, of course. So I was just curious how it works, how the Jack is creating Lambdas. So how it works under the hood. First of all, we have very simple code. We have, let's say, class, and this class has, you can see that hopefully, yeah. So this class has execute method that is executing runnable. Runnable, why runnable? Because it's super simple, has run method, perfect for Lambdas. And let's imagine that we have two static methods, main and main2. The first one, as you can see here, it's using anonymous class, right? I'm creating anonymous class in here to execute runnable, and in here I create class, and I'm using Lambda. So I basically created a file and compiled that with Java 8 and Jack and look at the generated bytecode, Java bytecode and DEX bytecode. How it went? Quite cool. That's how your code looks like when you convert it into bytecode. Basically, this is, once again, this is this very very simple class. Basically, I'm just creating an instance of a class, and I'm executing code as Lambda or as an anonymous class. And more or less, it looks like this. There is a tool from Oracle, part of JDK, that you can convert, I think it's called Java P, and you just basically take that class file and convert into something like this. And this code is, of course, straightforward. You just create a simple class, then you make a duplicate, because you need to call invoke special to call constructor. So you need to duplicate to have the reference after you invoke special, because you lose the reference. Remember, we are on the stack-based virtual machine. Then we need to create another instance on Java class. This is the part I marked with red. So we need this anonymous class, which is inside, right? Then you run enable. This is the anonymous class. I need to invoke special once again, and then at the end I'm executing this runable. So this is how anonymous class and Java 8 look as a bytecode, right? More or less like this. Oh yeah, this is this anonymous class, like I said. How it looks with Lambda? A bit shorter. Instead of creating, let me go back. Instead of creating this red part, a new class, I just call invoke dynamic. See the difference? Green, red, green, red. Okay. There is special instruction, invoke dynamic. It's for lambdas. I think it was introduced in Java 7. Anyway, it's a part of one of the instructions in the bytecode. And thanks to that, this is how Java 8 is executing lambdas. As you can imagine, the special instruction most probably is more efficient than creating an anonymous class, because there is less instruction to be used and whatnot. And actually, I tried to understand the efficiency of invoke dynamic and got lost somehow. But it's an interesting topic, and Java geeks were talking about that like a few years ago, when it was brand new stuff for Java, which is now new stuff for us Android developers. But then with Java, we have this invoke dynamic thing. And now let's look at the Jack. With Jack, our code with the anonymous class look like this. As you can see, it's very similar. The difference is that we had new instruction with bytecode. Here is new instance instruction. But still, I need to create a new instance. Then I need to invoke direct, call a constructor. Then I create another instance of internal class, call another constructor, and then execute the execute method. Okay, I need like six instructions for that. That's Jack with anonymous class. And this is how Jack works with Lambda. Do you see the difference? There is no difference in instructions. The only difference here in the left part, the name of the anonymous class. With Jack, it's called void main2 lambda impl 0. Without Lambda, it's just 1. So the bottom line is that Jack is doing nothing extra for lambdas. It's basically sugar syntax, so to speak. All that Jack is doing when you go with Lambda is creating this anonymous class for us. So I could just simply, sorry for going back, so I could just simply create this class like this. Or if I go with Jack, Jack will convert this thing into anonymous class here. No magic here. Basically, I can imagine a plugin for IDE, let's say for Android Studio, that is converting lambdas back to anonymous classes. The reason for that is, sadly, there is no, let's say, invoke dynamic in an Android virtual machine. It is in Java, because I guess they can easily upgrade the Java virtual machine on your machine if it's a server. It's not so true with a mobile phone. So sadly, lambdas, even with Jack, that's just nothing really different. Oh yeah, that's another pretty chart with animation. So like I said, with Java, anonymous class, with Jack here and here. When I go with, when I create this anonymous class, it's simply anonymous class, which is quite obvious. If I go with Java, I have this invoke dynamic for lambdas, and sadly, it's just anonymous class. So thanks, Google, for those language features, but at the end, it's nothing really cool. But there is something which is really cool with Android, new Android. I think it's part of NPreview 3. So quick history. So we had Dalvik on Android back in the day, and Dalvik was interpreting our application, and there was just-in-time compilation. So we started our application. It was being interpreted at first, and then just-in-time compilation kick in to make things faster. That's how Dalvik worked. Then Google decided to, oh, sorry for that, I'll just skip the boring part. Sorry, not this slide. Okay, or maybe I should go back to that. Okay, sorry. On the left, this is Dalvik. So interpretation and just-in-time on old Androids with Dalvik. Thanks to that, we have low memory footprint, poor performance because it's a bit slower when you have to, every time when you start the app, you have to interpret the same code, then you have to wait for the just-in-time compiler to kick in. Every time when you start the app, the cycle over and over again. And back in the day, even I think the unsophisticated garbage collector, it's not. I'm telling that their code is not that good. This is how they describe their own work. So Google is not very proud of their early version of virtual machine. And also, as you maybe remember, Dalvik needed 2 pauses to free your memory. One pause was needed to stop the whole application to find which parts of memory are not being used. And then there was another pause to remove those parts that were not being used. That was with Dalvik. With DR, they decided to change that into ahead-of-time compilation. So when you install your application on your phone, it's being compiled into native code for the architecture of your phone. So let's say if you have an ARM processor on your phone, your application is being converted into ARM code. On an Intel phone, your code was converted into x86 assembly. That's how ART was different from Dalvik. So when you pressed icon on your phone, the application was executed from the compiled native code. Another difference with this approach, with dart, was that they could actually take the code and apply some optimizations because they were compiling in advance your application. And then, of course, performance is way much better. And of course, better GC algorithms were introduced over time. So this is oh yeah, and another funny thing, with dart, there's only one pause. So if I want to free a memory, I just go and mark parts that are not being used on the fly when the application is being executed, and I only need to pause the application to remove those parts that are not needed. I don't need 2 pauses for that. So on your left is old Dalvik, then there was the new art, and then we have basically mix of both. So we have interpretation, just-in-time compilation, and ahead-of-time compilation with the new Android preview and preview 3. How it looks like now. It's still called dart, but we are, like I said, back to just-in-time compilation. Now, there is no need to compile the application at install time. So as you maybe remember, I think I have a slide for that. When you start your phone, there is this screen with optimizing app, right? So there is no need for that anymore. Another thing is that when you update your system, you don't have to recompile all the apps because Android is a Linux. Your application is using, let's say, SQLite or libSSL. And every time when you are updating Androids and those libraries, you have to recompile your native code. So that's why there was this optimizing app screen every time when you were upgrading your Android. And the funny thing about that is that there was a presentation about security during Google I/O, and there was a guy from Google security team, not from Android security team, but generally from Google security team. And he said that their approach is to push updates, security updates, on any kind of updates as often as possible. But I'm not updating my phone when I receive an update because of those all slowness on waiting for reboot and whatnot. And by removing this optimized step, for instance, for me, updating my phone is basically, okay, I can do click and have my phone back in 5 minutes or 4 minutes or whatever. One of the reasons why Android is changing this approach is also because of that, because they want to ship updates as often as they can, so that the user are not actually ignoring that because it takes time to apply those changes. So now with Android, we have hybrid of both worlds, just-in-time compilation and ahead-of-time compilation. And idea is that when you start your application, you want to have a fast startup. So applications start with just-in-time compilation. And then eventually, in long run, your application is going to be converted into native code, which is, I guess, super cool. And there is no need for that screen, hopefully. I'm not sure, to be honest, because I'm on Marshmallow, but if someone has npreview 3, most probably there is no such screen anymore. And how it works there is animation for that, guys. It's marvelous. More or less, it started like this. On our phone, we have application, and then let's say that's a Facebook app. I click on the app, and basically, the art, so the new runtime, is using the old, let's say, approach for interpretation and just in time to execute my app. The app is running. So on Facebook, I'm going to main screen activity. I'm playing with this app, but let's say I'm only using main screen activity and a chat. I'm not going into group features. I'm not going into gallery. I'm not going into settings. Anyway, I'm playing with the app, and there is a separate thread being a part of my application, and the thread is dumping information, what I'm actually doing in my application. So when I'm playing with Facebook app, this thread is writing profile files information. Alek is on main screen. Alek is maybe sometimes in gallery. Alek is not using this and that and whatnot. Those profile files are being read down onto disk, okay? And then there is a separate service, which is a system-wide service, and this service is when the phone is in idle mode, whatever it means. The service is going through all those profile files and is compiling those parts of your application. So if we have this Facebook application, it has like tons of activities and whatnot, this service will go and take main activity and all parts that are needed for main activity and compile that into native code. So I have a bunch of DEX bytecode and a tiny bit of native ARM code for main screen of my my application. And then it's being written as my app. So it's original app and a bit of precompiled native code for this application. So when I start the application again, now it starts a bit faster because there is no need to interpret the first screen of the application because already compiled. So it's using the compiled version in the native code. And of course, I'm playing with the app some more profile files are being written down onto disk. And because of that, more parts of the application are being compiled into native code. And then this service kicks in once again, and it's converting those extra parts of application that I'm using into native code. So this application, at the end, is even more compiled. It was pure DEX bytecode, and after a few runs of this application, it's almost native code. So if you use the application, you have fast startup, you don't need to ahead compile it, but if you use the application more and more, the more and more parts of this application and basically native code, and they don't need interpretation or just-in-time compilation. And this cycle goes over and over again. Of course, let's imagine that someone is updating his phone, so those compiled parts are not okay anymore because some parts of Android system have changed, like libraries and whatnot. What happens there? Just those compiled parts are being removed. And I go back to the first step, so my app is pure DEX bytecode, and I have to start it again and kick in the profiler and the process to compile that and get some more compiled application. But thanks to this approach, and that we still have on the phone the original bytecode, when the system is being updated or something changes, there is no need to optimize apps again, and we still have the benefit of executing of native ARM code. And I'm afraid, oh no, that's my wild imagination, sorry for that. But yeah, I think that's the last part, and I'm really proud of that. Like I said, I got this idea under the shower, and I think it's going to happen next year, Google I/O 2017. So this is a typical company, Team A, Team B, Lonely Wolf, external developer, of course, our DevOps and Office Manager, our best friend, source repository, and our another best friend, continuous integration system, right? And I, as an Android developer, I'm part of this team here. Yeah, that's my forehead. Anyway, my work looks more or less like this. There is some source code in the GitHub repository, right? And I basically have this source code everywhere in the company, and even the continuous integration system, it also has the source code, right? Basically, this is the starting point. You are working on a project, everyone has the same code. And let's imagine that we have compiled this code already, okay? And then now, let's say that Team A will gonna work on UI, and I will work on better networking or whatever in my application. So Team A is gonna create some new source code. and then even gonna compile the source code on their Macs or maybe ThinkPads or whatever. So they have the right code and compiled on their own quite slow computers. And then I and my team, we create some more source code and we also compile it on our Macs or wherever. It takes time, but anyway, we did the work. What happens next? Of course, we push the code into repository. And the next step, what will happen? Of course, continuous integration. Jenkins is gonna pull the source code, and Jenkins is gonna compile this code again. So not only I compile this code, not only the team that's sitting there next room compile the code, also Jenkins compiled this code. And of course, this lonely wolf, he just joined the company or got a new ticket to do, and he's pulling all the code from a Git repository, and this guy is also compiled this code again, which is I have fast Mac and I have lots of other things to do at the office, but I can imagine that all this work could be optimized a bit. And let's imagine such a scenario, that we have cool Jenkins, basically with a jack, so a compiler in a cloud. And then all the source code is, again, everywhere. And of course, we are still working on some new features. Some new code was written, and now I press build button or compile button or run button. What happens then? Then my source code goes straight to the cloud. Then Jack, which is of course super powerful server somewhere in the cloud, is compiling the code. And then I'm just getting back the artifacts. The team and I am getting back the artifact. I don't use my computer as a machine to compile stuff. I'm just basically using it as editor. The whole process is happening in the cloud on Jenkins using Jack as a server. And then when we push the stuff into Git repository, and this guy pulls the code from the Git repository, and he builds the stuff, he will get all the artifacts that are prepared, compiled already from the cloud. So looks quite cool, pravda? All right. And the question is, how feasible the idea is. So of course, it's already done by Facebook. It's called Bug. There is a video on bugbuild.com website, and according to this guy in this video, it's in 35 into this video, 35 minutes into 34 minutes into this video. So according to this guy, at Facebook, every developer is basically compiling 93% of his time is compiling the same stuff over and over again. And what's quite interesting, this applies to whole company. That's why they created the bug build system, and if I understood the video correctly, they use Cassandra. All the computers are basically pushing artifacts into Cassandra, which is a key value store on their servers. And all those artifacts are being pushed from the developers or being kept pushed from a continuous integration service into Cassandra. So if I need to compile something, I don't have to build on my computer. I just get the artifacts from Cassandra. And if we get back to Jack, I check Jack sources, and Jack is basically in client-server mode. So there is, if you fetch Android open source project, there is Jack's directory there, and in this directory, there's a file called jack.sh, which is Jack shell script, and all this shell script is doing is taking file and using curl command and posting this file to Jack server. So you are able to start Jack as a server. Now it works only locally, but I guess it's a matter of time when they will prepare cloud solution, so that basically the communication between computer that is requesting the compile process, so to speak, is over HTTP. So I can imagine that this scenario is really possible. And like I said, it's going to be introduced during Google I/O 2017. I'm 100% sure. 93% sure, okay, 93. And actually, I wanted to end my presentation with this wild idea, which is possible, and source code is there in the cloud. If there are any questions, I was told by Jonathan that he's gonna give his T-shirt if there is any question. Not the one that he's wearing, the other one from the previous.